This video is on factoring quadratics. I'm going to specifically be looking at factoring the greatest common factor and factoring difference of squares. The greatest common factor is the first thing we always look for. So the directions up here, it says to factor completely. These are the directions. I'm going to highlight this in pink. Factor completely. First one we're going to look at is GCF. I'm going to highlight this in green because this is the topic I'm focusing on. When we factor the GCF, we're actually going to put that GCF, the greatest common factor, on the outside of the parentheses. So we're going to put the GCF on the outside of the parenthesis sets. So again, the parenthesis sets are going to make it to become multiplication. So factoring is really dividing because we're going to be writing them as a multiplication. So that means we have to divide to make it look like multiplication. We're doing the inverse. So let's determine what our GCF is of this first problem. So again, GCF is the greatest number and or letter that can go into all terms and can be divided. Each of these terms can be divided by it. So if we look at this first problem, we have 9n squared minus 24n. So if we look at our number first, we actually look at our smaller number because we know nothing bigger than 9 can go into 9. So 12 can be multiplied by 2 to get 24, but I cannot divide 9 by 12 and get a whole number. So I want to find the greatest whole number that'll go into both 9 and 24 that I can divide 9 and 24 by. That's why we look at the smaller number, because anything bigger than 9, I cannot divide 9 by it. So 9. 24 cannot be divided by 9, so that is not the good number. I then think about my factors of 9. I know it's 1 times 9, then 3 times 3. Those are all the factors of 9, so I focus on the biggest and I work my way down because that's why we want the greatest. So I just check 9, and 9 does not work in 24, so it's not common. So then my next number would be 3. 9 can be divided by 3 because, again, it was a factor of 9. 24 can also be divided by 3. So therefore, the greatest number so far is 3. So I'm going to put up top. So far, our greatest common factor is equal to 3. That's the number. But as you can see in both of these terms, there is a letter, and they're the same letter. That means that my greatest common factor will also include a letter. Now, just like we look at the smallest number for our greatest common factor, we also look at the smaller exponent. Because if I'm going to divide letters, I have to subtract the exponents. Now this one has n squared. I only have n to the first power here, and I cannot do 1 minus 2 and get a whole number. So I need to make sure that I look at the smaller exponent, which is n to the first. I can take 1n away from here, and I can also take 1n away from here. So it has to be the greatest common, and I have to be able to divide it. So I can take 1n out of both of these. So I can have my GCF has an n in it. So my greatest common factor is 3n. So what we want to do, we've just found the greatest common factor. To actually factor it, we have to divide each term by the greatest common factor. So on this problem, I'm going to divide the 9n squared divided by 3n. I'm going to divide this 24n by 3n. Now up here it says put the greatest common factor on the outside of the parentheses because when it's on the outside, it would be a multiplication of the factors. This is a factor because it's the greatest common factor. Factoring is rewriting an expression as the product of its factors. This is one factor of this problem. What does 3n multiply to give me the original problem? That's what we're doing. So I'm going to put my 3n on the outside of my problem, on the outside of a parentheses. Then we divide. 9n squared divided by 3n is 3n. I keep my sign because a negative divided by positive is still a negative. 24n divided by 3n is just 8. because I took that n away from the 24. Now, I do have to always look back inside my parentheses. This is just GCF, so I should not be able to factor it any further. But inside my parentheses, I have two terms. One term, second term. Back from the chart, we want to look for a difference of squares. Is 3n a perfect square? No. So automatically, I can stop there. I know that this has to be my final answer because I cannot factor anything any further. So this is my answer. And I know that this is my answer because this is a product of the factors of 9n squared minus 24. You can also think about that as if we were to distribute this back through, would we get the original question? So if I distributed this back through, 3n times 3n gives me 9n squared. 3n times negative 8 gives me negative 24n. So yes, this is correct, because I know if I distribute it back through, it'll give me the original. So I'm going to go a little faster on this next one. We're going to look for our GCF. This time we have three terms. So we have to make sure we look at all three terms for it to be common. So again, look at our number first. The smallest number is 4. So I look to see, can everything be divided by 4? 4 can, 20 can be divided by 4, and 12 can be divided by 4. Therefore, my GCF right now is a 4. Then I look for letters. I have an X, no X. So because it's not common, I know my GCF does not have a letter with it. So my GCF is only 4. That means I can divide all of my terms by 4 because that's the common part. And we can write out we're going to write out our GCF on the outside of a parentheses, and then we're going to divide. 4x squared divided by 4 is x squared. 20x divided by 4 is positive 5x, and negative 12 divided by 4 is a negative 3. Close parentheses because that was the end of the problem. Now, we do have, inside the parentheses, we have three terms, and this is when we would look for, can we factor this further? I would use guess and check for this, which, again, because this is GCF, this should not factor further. And I'm going to go ahead and let you know that this one will not factor further. I'll get into guess and check in a later video. So I'm going to box this up, say that this is my correct answer. And I can also check to make sure that this gives me my original. Distribute 4 times x squared is 4x squared. 4 times 5x is 20x. 4 times negative 3 is negative 12. So yes, this would give me back to my original. The last GCF problem I'm going to do is 4w squared plus 2w. So again, GCF. We look at our numbers first. We have a 4 and a 2. So 2 is my smaller one. Can 4 be divided by 2? Yes. 2 can be divided by 2? Yes. So GCF right now has a 2. Then we look for letters. I only have two terms, so I have a w squared and a w. Both of these have the same letter. And I look at the smaller exponent, which is w to the first. So my GCF is w to the first. So now that we have our GCF of 2w, we can divide all of our terms by the GCF. I'm going to put that GCF on the outside of a parentheses. Now I'm going to divide. 4w squared divided by 2w is 2w. I'm going to keep my sign because a positive divided by positive is a positive. And then 2w divided by 2w is 1. A lot of people will actually just cross it out and say we don't need it anymore, but you do. Because as I've shown you on these other ones, if you distribute, it should give you your original. To distribute this, I would do 2w times 2w. That gives me 4w squared. Then I'd have to do 2w times 1. That's how we get the 2w. If you look at this and say that, no, I can get rid of that, and I distribute that 2w, we would only have the 4w squared. So then it wouldn't give us the original problem. That's why we have to make sure we do say that it is plus 1. So this is our final answer for number 3. So GCFs, this is always the first thing you do. So even on these next problems that we're going to be doing, you have to find the GCF first and then continue it. because here we still have two terms inside this problem. We would look to see if this could factor further. On the chart, two terms means difference of squares. So is this first term, 2w, a perfect square? It is not. Because 2 is not a perfect square, automatically we can just stop there and say this is done. So if we move on to this next one, it is the difference of squares. So we still will always have to factor our GCF, but then we will look for anything else that can factor. So a difference of squares follows the pattern of you have a perfect square, I'm going to call it a squared, minus, because it's a difference, and then we have to have another perfect square, which I'm going to call b squared. So a squared minus b squared. This will actually factor to, and this will always happen if it's in this format, we take the square root of a squared, that is a, plus we take the square root of b squared, which is b, parentheses, because I'm going to have two factors. I take the square root again, we have a, but now instead of plus, it's going to be a minus. And then we have our square root of b squared again, we get b. So in order to get the a, the first terms, and then the second terms, we take the square root of the first term to give us our first, take the square root of our second term to give us our seconds. We have one positive, one negative. Now if you put the negative and then positive, that's fine. Because when you multiply something, if you put them in a different order, it means the same thing. The entire parenthesis set. Because if I were to say 5 times 2 or 2 times 5, gives me the same answer. So again, we take the square root, because they're perfect squares, square root of this first term, the square root of the second term. So let's go to this first problem. We need to find our GCF. Always find your GCF. The smallest number is actually a 1, because there's a 1a squared. So GCF is a 1. Everything can be divided by 1. Both of these do not share a letter, so our GCF is just 1, and that will not affect the problem at all. So I don't even need to divide by the 1. I don't need to write that 1 on the outside because it's technically already there. So here, now that I still have two terms, I look for a difference of squares. I look at the first one. Is a squared a perfect square? Yes, because a times a is a square. Any even exponent is automatically a perfect square. So if it was a to the 8th, it would still be a perfect square. Then I look at the second term, 36. Is 36 a perfect square? Yes, 6 times 6 gives me 36. And then difference. Is it a subtraction sign in the middle? It is. Therefore, this is a difference of squares, and I can factor this using this pattern. So if I take the square root of a squared will give me a, and then the square root of 36 gives me 6. This will give me my first terms, so the parts in the beginning, and this, since this was my second term, it'll give me the parts at the end of our parentheses. And because our GCF was just 1, I don't even have to put that on the outside. I'll have my parentheses. I'm going to put a, because my first term, plus 6, close parentheses, open parentheses. Notice I don't leave any space between them because this is a multiplication. I put my first term back in there, a, but now it's minus, and then my second part of 6. This is our difference of squares. If I were to distribute this back through, I would have a times a is a squared, a times negative 6, 6 times a. So that's negative 6 and positive 6a, which will go to a 0. Notice I have no a value in here, just basic a, because it's gone. And then we have a positive 6 times a negative 6, which gives us the negative 36. This is why those signs have to be different, because we are literally getting rid of that middle value. Instead of going from a squared to a to a constant, it's going a squared straight to a constant. So if we look at this next problem, again, GCF, that's the first thing we do. Our smallest number is a 3. Can 48 be divided by 3? It can. So we have our GCF is 3. We only have one letter in this problem, so there is no GCF of a letter. So now we have to make sure we divide everything by that GCF of 3. And we're going to put it on the outside of the parentheses like normal. 3x squared divided by 3 is x squared minus, because negative divided by positive, 48 divided by 3 is 16. Close parentheses, because that was the end of the GCF. Now there is still inside of our parentheses, we have two terms. We look for a difference of squares. X squared is a perfect square, 16 is a perfect square, and we do have a subtraction sign. Therefore, we can do a difference of squares. We take the square root of x squared, which gives us x, and the square root of 16, which gives us 4. So now we can write our answer. We have to make sure we have our 3 on the outside of our parentheses because it is the original GCF. Open parentheses. I need the x and the 4 inside of each set of parentheses. So I have x plus 4, parentheses, and then x minus 4, close parentheses. And again, there's no space in between these two sets of parentheses because this is multiplication. I'm going to keep going. Number 3, we're going to look again for our GCF first. Our smallest number on here is 12. 75 cannot be divided by 12, so we need to find the factors of 12. We know that 1 times 12, 2 times 6, and 3 times 4 will give us 12. I go in order so I can see the smallest all the way to the largest. 75 cannot be divided by 12, so this one is gone. 75 cannot be divided by 6, so 6 is gone. 75 cannot be divided by 4, so 4 is gone. 75 can be divided by 3, so 3 is our part of our GCF. Again, I went in order because I wanted the greatest number, so I went down in value as I kept going. So GCF right now has a 3. Now I see that both of these do have a letter. They both have the same letter, so I know I can factor out an x. I look for the smallest exponent, which is x to the first, so I know my GCF is 3x. Now I'm going to divide all of my terms by that GCF of 3x. I'm going to put the 3x on the outside of the parentheses. 12x cubed divided by 3x is 4x squared. Negative 75x divided by 3x is a negative 25. And then the x's are gone, so close parentheses. That's our GCF. Now, because we do have two terms inside the parentheses, again, we look for difference of squares. 4x squared, this is a monomial, so are all parts of this a perfect square? 4 is a perfect square, and x squared is a perfect square. So this is a perfect square. 25 is a perfect square. So we have two perfect squares. And we have a subtraction, so we have the difference. That means that we can factor this using the difference of squares. So I'm going to take the square root of 4x squared. Is going to give us 2x. The square root of 25 is 5. So now we can write our answer. We're going to keep the 3x on the outside of our parentheses because that was our original GCF. The 2x and the 5 are what are inside the parentheses. So we have 2x plus 5, close parentheses, open parentheses, 2x minus 5, close parentheses. And again, you can have 2x minus 5 and then 2x plus 5 if that's what you would like to have. This is the same thing. Because in multiplication, it does not matter in which order you go, just as long as you have the correct terms. This last problem, number 4, is 25 plus 4x squared. The thing about this is that we like to have our letters first. This is a constant, this is a quadratic term. So we actually want to rewrite this to become we have a positive 4x squared. We're going to rewrite it as positive 4x squared first. And then we do have a positive 25. So this is actually how we should rewrite this. Now we should be able to factor something. So we look for our GCF first. Our smallest number is 4. 25 cannot be divided by 4. So we know it's 1 and 4 and 2 and 2. So we know 4 does not work. 25 also cannot be divided by 2, so 2 is gone. Well, this is also 2, so this one's gone. The only thing left is 1. Everything has a GCF of 1 no matter what, or everything can be divided by 1. So if there's no other numbers that can work, then GCF is 1. That's okay, because we could still look for a difference of squares. If this does not factor further, this answer will have to be prime. So we look to see, is this a difference of squares? 2 terms. 4x squared is a perfect square. 25 is a perfect square, but it is not a subtraction sign, so this is not a difference of squares. The GCF was 1, and this will not factor further. So the only thing that will give us the original is 1 times the problem. That means that this is prime. If this problem had a GCF of 2, then the problem would not be prime. It would just be 2 parentheses 4x squared plus 25. So it's only prime if the GCF is 1 and the problem cannot factor any further at all. There is no such thing as a sum of squares. So I'm going to put a note down here. A sum of squares, which would look like a squared plus b squared, cannot factor at all, except for the GCF. So again, if we had a GCF of, say, 2, then this would be factorable. But because the GCF was 1 and it was a sum of squares, it was prime. And I did not mention this yet, but if you notice, all of the beginning terms, the leading coefficients, even when we rewrote this, they were positive. If you ever have a leading coefficient that is negative, your GCF should include a negative.